engineering science. Covers what I'm going to do. The electrical covers learning outcome 2. Learning outcomes to investigate and apply direct current DC and alternating current AC theory to electrical circuits. So Kieran's passed it, so he won't be in that class. He will be in your own with OMAL for mechanical science in semester 2. Yep. So OMAL will deal with that. The assessment for the electrical half is a practical investigation lab report worth 20% of the overall mark for the module, and an examination of 1 hour worth 30% of the overall mark. So that's 50 in total, and then OMAL's learning outcomes make up the other 50%. Yep. Okay.
It'll make up the 20.
So he'll have an assignment as well, and I believe that's kind of a practical thing, I think. Yeah, do some tests on some materials, I think it's happening, isn't it? And an examination on mechanical principles as well. All right. So start from the very beginning, and I do come in quite low because sometimes get people come on a course that really have done very little electrically before they come on this course. So voltage, it's the pressure applied to the circuit. Think of it as the force that pushes the current around the circuit. Designated by the symbol V, although you'll see others used symbols on it, like potential difference, EMF. U is a symbol used by the Germans to represent a voltage, okay, and that's measured in volts, okay. E you'll also see used. You'll see me use that one occasionally. All right, can be found to be given different names. Potential difference, the difference in potential between 2 points. Electromotive force, usually used when considering generated voltages or the operation of motors. Yep. Key point here is that current flows in a circuit or a component because of a difference in the applied voltage at either end of the circuit or component. No difference, no current. So if you connect 12 volts to both sides of the resistor, you won't get no current flow. You have to have a difference in the 2 points for current to flow. All clear on that? Yep. Second key term. One thing about voltage, I will pull you up. If you say there's 10 volts going through that resistor, Mike, I will tell you, no, there isn't. Voltage is across, current goes through. Yeah. So the current is a measure of the rate at which charge is flowing in a circuit, designated by the symbol I, and is measured in amperes, shortened to A, shortened to amps, okay? I'll also pull you up and have a bit of a fun about it if you say the amperage is, because that's not a term that I normally associated with. Yeah, welders say that kind of thing, stick the amperage up. But us scientists, electricians say put the current up. Resistance. The resistance of an electrical circuit, and a little bit later on in the module you're going to learn about impedance, which is AC resistance. Alright? It's a measure of the opposition or restriction to the flow of current, designated by the symbol R, and is measured in ohms. When a current flows through a resistance, in its most basic form, electrical energy is converted to some other form of energy, such as heat, light, or the rotation of a motor. All parts of a real circuit have some resistance to flow, and without it there would be no conversion of or use of electrical energy into another form. So no resistance means no work done. Yeah? Okay? Okay, and it applies all the way through. Even when things get more complex, Ohm's law is always obeyed. The circuit always will obey Ohm's law. Defines the relationship between the applied voltage, the resistance of a circuit, and the current that flows in it, such that the current is equal to the voltage divided by the resistance. And that's the normal way round, because the current will flow dependent upon the voltage that you apply and the resistance of the circuit. Yeah? You vary the current by altering V and or R. Alright? You could substitute E for V, where sources of EMF are being considered. Alright? But it's still that way round, and it can be arranged electronic and technical. Right, an hour long. So what you've got there, formally is now N2 I, V and R. Right, an example problem for you, fairly easy one. 75 volts applied to a resistor. So what formula are you going to use? R is equal to V over I. So, and I do like people to get that habit of writing the formula down, putting the numbers in. So V is 75, R is 15, and then putting the answer. 75 over 15 is 5 ohms. Yeah, units are important. You will lose marks in exam if units are supposed to be there and they aren't included. Won't they, Kieran? Alright, over the page, example problem 2. Find the voltage required to be applied to a circuit of resistance 16 ohms to make a current of 1.5 amps flow through the circuit. Also calculate the power dissipated in the resistor. I'll let you have a go at that one. So how have we gone about this then? Okay.
Well, the first one's 1.5 amps times 16 ohms.
Yeah, so V I times R. What's that? 1.5 16 equals 24 volts. Yeah?
And I use the power equals I squared times R.
1.5 squared times 16 equals 36 watts. Kieran went IV, power equals IV, yeah, equals 24 times 1.5, 36 watts. Right, both correct, no problem with that at all. However, in other cases, there's a reason why I'd choose the way Daniel did it. And that is, Kieran's method uses a calculated value. Yeah, so you can't always just use given values, but if you can, it's recommended to. Your method has used the two values I and R given in the question. That 24 volts could have been 24.367825793, which you then round to, let's say, 3 or 4 significant figures. You're then carrying that error into the next part of the question. So if you can avoid doing that, don't do it. There are instances when you start getting meg ohms involved or milli, you can make quite big errors by compounding them. Yeah? Okay? I mean, in an exam question, it's unlikely that you're going to lose marks, but it's just good practice to use given information wherever possible. Alright? In that particular instance, that didn't matter, but it could do if there was rounding involved. Alright? Rounding something that you need to think about as you go through the module. Rounding to sensible values. Sensible number of significant figures. If you're taking measurements using an instrument and you measuring to 3 significant figures, if you then go and do a calculation with that measured value, it's not appropriate to include 5 or 6 significant figures in your answer. 3 the lowest in your data, the highest in your data would be appropriate. And in general, for my answers, 3 or 4 significant figures would be plenty. Okay? Just before I get you to have a look at the tutorial questions in the basic electrical calculations handout, just have a quick look at, I'm sure you're both familiar with these anyway, but the unit multiples and submultiples system for engineering. Giga, 1,000 million, or 10 to the 9, e.g. 10 gigawatts is equal to 10 times 10 to the 9 watts. I'm going to correct my own self there. That should be a lowercase k volts. Uppercase K is the computer killer, which is 1024 kilobytes, for instance. Right? Milli, 10 to the minus 3, or 1,000th. Micro, a millionth, 10 to the minus 6. Nano, 10 to the minus 9. Pico, 10 to the minus 12. And the last two, I remember the order by, they go in alphabetical order, N and P. Alright, and you're going to come across those in capacitance mainly. You'll get currents down to micro, and even microvolts. Yeah. Pico and nano are going to be capacitance, really, because a farad is a really, really big unit. Okay? I can, a set of worked solutions to tutorial questions will also go up on Brightspace. Alright? So the ones you don't get a chance to do. And it could be my usual, like